Yes, and we're back live once again on a Tuesday. Ah, man, it just blows my mind. This is the third time that our school has had to go virtual for 2 weeks. You would think that a giant group of students would know better than to, get together and hang out. And oh, one bunch of us tested positive for COVID. Oh no. Like, it's like frustrating and annoying. Anyway, I'm going to get off my soapbox. I'm just giving people a moment to get in. I see 12 of you have jumped into the stream so far. Giving you an opportunity just to kind of get in and wake up on this glorious Tuesday morning. Just as a reminder, for those of you who are here so far, if you would leave a comment in the chat for me, that would be fantastic, so that I have it for my records, so that I can look back and be like, hey, that person was present, and that person was present, and I was present. You could say I was there. But anyway, there they go, as they're throwing in their comments into the chat. Well, at least 4 of them so far. A bunch more, I assume we'll do it in a moment. There they go, as they're typing that out. While you guys are doing that, and while I'm waiting for people to get in, let me explain to you exactly what we are going to be doing today. First, and I'm just double checking this right now, the time that I had the due date on it. Yep, there it is. I had a homework assignment for you guys, page 465, where I gave you 6 problems to get done. Oh, there are all my comments. They all just popped up. Sorry. But yeah, page 465 was due this morning at 7 o'clock. The first thing that I would like to do after introductions is I would like to go over a couple of those problems from that homework. Not all of them, but at least a couple of them, just so we have clarification if need be. I do have a couple in mind, but I would give you guys the opportunity to choose once I give you that opportunity. Then I would like to proceed with making a connection in our notes. There is a connection between this current chapter that we are working on and the next chapter that we're going to be doing, and they are definitely an intertwined connection, but we will get there when we get there. That would be fantastic if we did. So what I'm going to do is I'm going to transition over to my desk, and you'll be able to see what's going on up in here. And while I'm making this transition, I'm going to ask you from the homework, because obviously if you've already turned it in, fantastic, but I would like to clarify anything if need be from that particular assignment. So if you would pick a problem, and you can throw this kind of into the chat, and I'll kind of pick like the most common problem, but pick a problem from the homework where you would be like, yes, please, go over this one, help, please, kind of situation. Now, I do have a couple in mind, but I want to pick what you guys have to do first. I'm going to transition over to my desk. Now, keep in mind, I will still be able to see the live chat because I do have the video open on my phone, so I would be able to see what the heck is going on here. Oh, there we go. And already 3 people have picked number 36, so let's go ahead. I mean, I'll start there, definitely, but let me get myself set up, and then we'll kind of go from there. So, flip the camera over. Bring this guy up. Page 465, number 36. Now, I did make mention on number 36 that the actual problems were on the next page, but that is neither here nor there. Let me just make sure that I got the right. There we go. I put a bunch of Post-its in my book so that I could bring this thing up. But we'll get this thing going. Okay. Oh, I do need one more thing. I do need this thing right here. There we go. Excellent. Okay. So let's just familiarize ourselves with the problem. I'm going to zoom in on this sucker right here. Number 36. Again, I do apologize for the glare. Do this. There we go. And let's talk about it. In Chapter 5, we saw the distribution of total compensation of the chief executive officers of 800 largest U.S. companies. The average compensation in thousands of dollars is $10,307.31, and with a standard deviation of $17,964 and change. Here's a histogram of the annual compensation in thousands of dollars. Now, right off the bat, before I even think of anything else, I'm just looking at this distribution and just thinking about the shape of it. This distribution is definitely skewed to the right, just as a side note. I haven't even read the questions yet. I'm just looking at the thing. It's definitely skewed to the right. It looks like there's a large number of people who were within that first bar. Just trying to see. So like 100,000, 50,000, less than 25,000 possibly. Yeah. Well, keep in mind it's measured in thousands of dollars. So, but yeah, there's a large number in there, and then probably a few over to the right. I don't know what the maximum is, or the range, or the interquartile range, or anything like that. Okay. Part A, describe the histogram. Oh, well, that's literally what I just did. Okay. Describe the histogram. I would definitely say it's heavily skewed to the right. Without any extra information, I might be able to surmise that there are some outliers out there, but I can't prove that without further information. I wouldn't be able to prove that there were outliers unless I had the 5-number summary, which this problem does not provide me with. So I can suspect that there are outliers, but I would definitely say it's heavily skewed to the right. You want to go, it has one peak if you want to go that way. Okay. Let me adjust my camera so I can move this thing up a little bit, and then I'm going to have to flip the page. There we go. Come on, screen, and freeze. There we go. Good. Then it says a research organization simulated sample means by drawing 30, 50, 100, and 200 with replacement from the 800 CEOs. Okay. They say with replacement. That kind of bugs me a little bit, but I guess with replacement would be the idea of they draw 30 and they got a sample of that, and then they put the 30 back, and then they randomly picked 50, and then they did the histogram, and then they put them back, and then they randomly drew 100. I think that's what with replacement is referring to in the context of this problem. The histograms show the distribution of means for many samples of each size. Okay. And then there, of course, on the screen, you can see the two histograms, sample size 30, sample size 50. Now, before I actually flip to the back page, again, I just want to remind myself and remind you guys as to what it is that we're doing in this chapter with increasing sample sizes. This problem is headed towards the fundamental theorem of statistics. This problem is heading towards the central limit theorem, which obviously they're the same thing. But the idea that as the sample sizes are increasing, the more and more the shape of this distribution should appear normal. Now, we saw the original distribution, which was just every CEO in that group of 800 or whatever. It was heavily skewed to the right. It was the Fortune 800 or whatever they want to call it. It was heavily skewed to the right. But then when they took a sample size of 30 and took an average, and you took a sample size of 30, and you took a sample size of 30, and you took a sample size of 30, and we all took a sample size of 30, and then we all plotted our averages up here. Now the shape is looking a little less skewed. It's still looking skewed, but it's looking less skewed. And then when they get to the sample size of 50, it's looking less skewed because the shape of that distribution is becoming more and more normal the larger the sample size go. Now, again, keep in mind, I just want to reiterate this point. The fact that, okay, sample size of 50. That means that if I took a sample of 50 and got an average. and you got a sample of 50 and took an average, and we all took averages of 50. And we took our individual averages and plotted them and created this histogram. Let me look at the other two, because I don't even know what the questions are asking yet. Let's turn that page. Let me unfreeze my screen so we can take a look at that. Unfreeze. And here are the other two samples of 100 and 200. And yeah, 100's looking less skewed and 200's looking less skewed. It's almost like this peak is shifting itself towards the middle, which goes hand in hand with the fundamental theorem of statistics. The fact that as the sample size grows, the distribution of sample means grows more and more normal. Oh, something else I find interesting. Hold on. Let me go back to the sample size of 30 and 50. Boop. Here we go. Something I find very interesting here. Look at the range on the bottom. Look at the range on the bottom of this histogram right here. With the sample size of 30, the range was 5,000 to 25,000. And then with the range of 50, it was 5,000 to 20,000. Something that's piquing my interest right now. Again, I don't even know what the question's asking. I try not to do that because I like to be surprised. I like to notice things before they even ask the questions. But the range on the bottom is actually shrinking, which implies to me that the standard deviation is also shrinking. If the standard deviation is shrinking, that means there's more consistency. Because if the larger the sample size that we take, the more likely that all of our averages would be closer and closer and closer together. Let me take a look at the other two on the other side here. There they are. Then it says, oh yeah, look at that. The range on the bottom, 6,000 to 20,000, and then 8,000 to 14,000. The range is getting smaller. The standard deviation is getting smaller. The means are getting more consistent. There's less variation. And that makes sense because the sample size is increasing. And the way that one calculates the standard deviation for this is by taking sigma over the square root of n, which, you can't see the sigma because it's blocked by that giant glare. So I'll move it down. Sigma over the square root of n, which would be the the sampling distribution standard deviation. Let's look at the question saying. Explain how these histograms this is exactly what I'm talking about. Explain how these histograms demonstrate what the central limit theorem says about the sampling distribution model for sample means. Be sure to talk about shape, center, and spread. I know that word spread, it got cut off there. But that's exactly what I just spent the last few minutes talking about. I didn't even look at the questions yet, or what they were actually asking of me. I just like to notice these things before I even get to the question, because it's a good exercise for knowing that you understand the concept that is in front of you. So if I was going to explain how these histograms demonstrate what the central limit theorem, which again, the central limit theorem is the fundamental theorem of statistics. You could talk about the center. I mean, again, I don't want to keep flipping back and forth between these pages. I froze the screen so that I could kind of do that. But the centers all tend to be about the same. If you looked at the centers of those four, they look really close to what the average is. The average originally they told you was $10,307.31. Again, in thousands of dollars. But the centers all seem to be about the same. They all seem to be about 10,000. I could talk about the standard deviation getting smaller. Thus, the spread is getting smaller. It looks like everything seems to be more consistent. I could talk about the range on the bottom. The variation, the spread go hand in hand with each other. I could talk about the shape of that distribution getting less and less skewed to the right as the sample size grows larger, or instead of getting less skewed to the right, you could say that it's getting more and more normal as the sample size increases. Yeah, solid. And then click, I gotta move up to C. There we go. Now, this question, again, it talks about a quote-unquote rule of thumb. I have not mentioned a specific rule of thumb for this problem. It says, comment on an off-cited, quote, rule of thumb that, quote, with a sample size of at least 30, the sampling distribution of the mean is normal. Well, even if I haven't commented on this quote-unquote rule of thumb, I wouldn't expect you guys to be able to reference anything like that. But let's talk about the sample size being large enough. That's what this thing is really referring to. With a sample size of at least 30, one of the conditions and assumptions, or conditions I should say, is that you have to have a sample size that is large enough. Yeah. If you're dealing with proportions, then you need at least 10 successes and 10 failures. If you're dealing with quantitative data, then that doesn't matter. But you do need to have a sample size that is large enough. Again, people argue, should it be 20? Should it be 30? They're going with 30 in this one. Well, as long as the sample size is large enough and all those other conditions are met, then we can assume normality. That's what the central limit theorem basically allows us to do. As the sample size grows larger, it grows more and more normal. So as long as we have a sample size that is large enough, then you could say that the conditions are met and you can assume normality. That's what the quote-unquote rule of thumb that they're referring to. But now it says, comment on that rule in regards to this problem. Because what they're referring to is, well, if I go back here to the sample size of 30, boop, I mean, it definitely still has major skewingness to it. It still has major skewingness to it. Generally speaking, if you have that sample size of 30, yes, it should look a bit more normal than this. But the reason why it doesn't look as normal as we would have liked it to, according to that rule of thumb, is simply because the original distribution is probably a ton more skewed than what typical skewed data would look like. Let me go back to the original distribution. Again, changing my camera over if this thing would move. There we go. There is the original distribution. And again, I don't know what these individual data points are. I don't know what the range is. I don't know what the maximum is. But my assumption is that that thing is like, since it goes up to 200,000 here, I would assume that there are some data points out here. They're just not showing up because, well, the vast majority of data points fall within this little block right here. This thing is skewed to the right. This thing is probably, well, the glare is in the way right there, but this is probably one of the most skewed pieces of data that we've ever seen. And I dare say that, well, I mean, there obviously could be more skewed data, but considering how skewed it is, a sample size of 30 still reflects that skewedness a bit more than what we would like it to. That's what the general rule of thumb is saying. If you have a sample size of at least 30, for the most part, you can assume that the sample size is large enough. But there are some real-life instances in which it's like, it's still a bit more skewed than I would have liked, which is what that sample size of 30 was showing. Anything else from that homework that we would like to talk about? I'm pretty sure I hit all the parts to that, but I know it was on the next page. A, B, C. Yeah, but it only went up to C. But are there any other questions from that particular homework before I put a close to this part of the class period? 16. Let's talk about 16. Let me bring the page back. Okay, hold on. And Yeah, I'm trying to get the page in the right position. Boom, boom. There we go. Nailed it. So, too many green ones? If you're one of those people that try to claim to me that you can taste the difference in M&Ms, then I'm sorry. You and I can't be friends anymore. A really large bag of M&Ms. The students in exercise 14, which I will have to go back and take a look at in a moment, found 500 candies, and 18% of them were green. Is this an unusually large proportion of green M&Ms? Let me go back to number 14 to see if there's any information there that I would need. So let's see here. Come on. So here's 14. Let's see. It says, suppose the class in exercise 12. Okay. Let me look back at 12. If I look back at 12, number 12 says that, okay, M&M's claim that 16% are green. 16% are green. That's the claim. That is the assumed population mean, for the lack of a better term. Okay. All right. So now, I'm bringing back 16 up on the screen so I can use that number in regards to this. Click. There we go. So they claim 16%. They claim 16%. Where's my calculator? Okay, calculator would be nice. There we go. The reason why I need a calculator is because I got to write some numbers up here. They claim 16%. So P is equal to I'm not even talking into the microphone. What am I doing? They claim that P is equal to 0.16. Now, with that population proportion, or the population parameter in place, we can assume a mean of the sample of 16%, which I'm going to get into a little bit more details to the context of that today. And we can assume a standard deviation of, well, I'm going to have to calculate it, 0.16 times 0.84 divided by the sample size of 500. Okay. And I'll calculate that in a moment. Now, okay. You found 18% were green. So your sample was 18%. They are claiming 16% with that particular standard deviation with a sample size of 500. And they want to know, is this an unusually large proportion? Now, I hear that phrase, unusually large. And I immediately think z-scores. Unusually large. That phrase should be in reference to z-scores. And what we've learned about z-scores in the past is that anything outside, or I should say outside, but more than 2 standard deviations away from the mean, either above the mean or below the mean, anything more than 2 standard deviations away from the mean would be considered unusual. Unusually large, unusually small, Derrick size, so to speak. So what we're going to do, I'm going to have to calculate that standard deviation, but I'm going to calculate a z-score using that 0.18. So let me do this real quick here. 0.16 times 0.84 divided by 500, square root of that answer. I got a standard deviation of 0.0164, I guess. 0.0164. So if I was going to calculate a z-score here, let me put a little piece of paper here so I'm covering up the rest of that problem. So the rest of my thing is readable. There we go. Unfreeze and there we go. Refreeze. Perfect. I would do something like 0.18 minus 0.16 divided by 0.0164. And that should give me the proper z-score that I'm looking for. Let's see what we get. 0.02 divided by that thing. Nice. I get a z-score of approximately 1.22. Now, that's not my answer. I still have to comment on what the question's asking. But if you found 18% green in 500 M&M candies, that would be a z-score of 1.22, meaning you are clearly above average. Is this an unusually large proportion of green M&Ms? No, it's not. It's not. Why? Well, because calculating the z-score, I got 1.22, which is within 2 standard deviations of the mean. This is stuff that's reaching back. We have to build upon what we've done in the past. I love this thing. So what I'm going to do is this. For the remaining problems that were on your homework, as I've done, sometimes I create a video to kind of review said problems so that you have an opportunity to see what you did right, what you did wrong. I'm going to do that. I wanted to at least do a couple of problems from the homework, and I will do a video reviewing the rest of the problems. So if you have not turned it in, which I do see that it does fall in line with some people. If you have not turned it in, please make sure that you get that thing done. In the meantime, ladies and gentlemen, if you do not already have them out, I'm going to need those notebooks out and open. Okay. Unface. Zoom out. There it goes. Good. There is one thing that has been bugging me since the last time we met on Friday. There we go. There's one thing that's been absolutely bugging me in regards to what I put into your notes. And so there it is. I'm going back in your notes to Friday. And I have to offer one correction that I absolutely need you to put in, or to change, I should say. So here are the notes that we started taking on Friday, where we took a Gallup poll of 1,785 adults. So it was based on the quizzes problem. And I wrote down this calculation to get the standard deviation of the sampling distribution. And there's one thing that I realized that I did after class on Friday, and I'm like, oh no, I did that. And it's been bugging me all weekend. I'm out on Saturday. This is all I'm thinking about. Watching the Super Bowl on Sunday. This is all that I'm thinking about. Shoveling snow. This is what I'm thinking about. I'm thinking about this one tiny little thing that I really do have to fix right here. Where's my red pen? I'll give myself a bad grade for this. Right there. That is wrong. And I apologize. And I would like you to fix that in your notes. And this is a very, very important distinction that I want to make. These are the notes from Friday, and I need you to correct something for me. The mistake that I made was that I put little hats on that P and Q. And it may seem silly. But in reality, those hats should not be there. Because when you are calculating a sampling distribution, typically, if you're calculating a sampling distribution, you are given a population parameter of P. You are given that P. You are given an assumed proportion. And then you take a sample. But when you calculate the standard deviation of that sampling distribution, when you calculate the sampling distribution, standard deviation, you do not use the sample P and the sample Q. You don't use those. you're supposed to use the assumed P and Q. And again, it seems very like it's such a minute thing, but it makes all the difference in the world. So what I'm going to do off to the side of this 0.0116, I'm going to draw a little arrow, fixing myself in a moment. Mind you, this is correct in all of your other notes. But it should be a P times Q over N. That's what it should be. There will come a time in which these hats will need to be there. But today, or I'm sorry, let me rephrase, this chapter is not that chapter. There will come a chapter in which these hats have to be there, but today is not that chapter. Or I should say, this chapter is not that chapter. Why do I keep saying today? I keep wanting to say today is not that day, like I'm giving a rousing speech where we're going to survive, but I can't promise survival. If there is an assumed population proportion of P, if there is one in the problem, then you have to calculate it like that. You have to. There are going to be problems in the future where you're not given that population parameter. And then you may have to do something like this. But again, this chapter is not that chapter. So that's been bugging me for a while. I say a while, it's been bugging me for 3 days. So, yay, I've corrected my little thing there. Okay. I got to give you some context to things. So this is sampling distributions continued. Today is the 9th. There we go. Now, I wanted to talk about what a sampling distribution is, what it means, what its consequences are. With an assumed population mean, comma, with an assumed population mean, that mean could be the population parameter of a proportion, or it could be the population parameter of an actual mean. It depends on if you have categorical or quantitative data. But regardless of what type of data that you have that mean. And sampling standard deviation. Now, this sampling standard deviation could be, and I'll put in parentheses down here, it could be the square root of PQ over N, which again assumes that you have that population P, or it could be sigma over the square root of N. Again, the difference between that is if you have categorical or quantitative data. If you have categorical data, you would be doing the square root of PQ over N. If you had quantitative data, you would be doing sigma over the square root of N in order to get that sampling standard deviation. With an assumed population mean and sampling standard deviation, we are trying to find the chance of a sample statistic occurring with an assumed population mean and sampling standard deviation. We are trying to find the chance of a sample statistic occurring, assuming that there is some truth, some concrete truth, meaning that population mean and standard deviation per se, maybe that sigma perhaps, or if you have categorical data, that PQ over N, because that P and Q are based on that population parameter. But assuming some kind of concrete standard of information, what are the chances that we would see such a sample statistic? Now, I don't know the actual numbers behind that Minecraft controversy that recently happened. So I'm just going to explain it to the best of my knowledge because this applies exactly to this. Recently, there was a guy in the Minecraft speedrunning community by the name of Dream, made a bunch of videos, got a bunch of kids to be excited about his videos. I don't care. Makes a ton of money probably. But recently, one of his world records came into question and was like, wait a minute. We know that the code for Minecraft has a certain drop rate for this item. And I'm going to make this number up. But let's just say it's like 5%. We know that the drop rate of this special item is 5%. Yet in this guy's world record run, he's not getting anything close to 5% in terms of a drop rate. Maybe he's getting like 20%. Again, making that up. I don't know the exact numbers. That's not the point. We know that the drop rate should be 5%. That's what the game is programmed to do. Yet this guy is getting 20%. What are the chances of that happening? What they did to calculate the chances of that happening are what we have been doing in this chapter. With an assumed population mean, meaning let's just say 5%, and a sampling standard deviation, meaning, okay, well, N is the number of trials that he went through. So again, I'm just going to make this up. Let's just say he went through like 25 trials. There were 25 opportunities for this dropped item. I'm just, again, making that number up. I want to see what happens. So based on this assumed population mean and this sampling standard deviation, what are the chances that this guy would get 20% drop rate? And what they ended up finding out was the chances of this happening were so astronomically small that it called into question this guy's validity. Now, he came back at it with a whole bunch of like math mumbo jumbo or whatever, but in reality, the original accusation still stands. I don't think he understands how statistics works. If he's trying to claim, like, oh, math guy, because the average person just looks at that and they're just like, I don't know what they're talking about. But anybody with a sense of statistical knowledge would recognize what they were trying to prove with that original mathematical paper. So let's write down some of that information in regards to what I just did here. With an assumed population mean and sampling standard deviation, we are trying to find the chance of a sample statistic occurring. Or with an assumed population drop rate of 5%, with a standard deviation here with 25 attempts, what are the chances that this supposed world record holder would get a drop rate of 20% or better? Let's find out. So hold on. Let's see. So first, assume now mind you, when I say drop rate, I'm referring to this special item in the game that happened that you get after you do something to an enemy. Again, I don't play Minecraft. I just know the details behind the math. Assume a drop rate of P equals 0.05. And the reason why they can assume something like that is because, well, that's what the game is programmed to do as long as you don't alter things at the beginning, which is what they think this guy did. There are n equals 25 trials of getting an item. I don't know, drop rate, item drops or something. I don't know, something like that. But there are 25 opportunities, let's just say. Again, making these numbers up as I go along. So there are 25 instances in which an item was dropped and this guy picked it up. And the drop rate that he's looking for is 5% to get this very special item or something along those lines. So let's see, this would be mu of p hat is assumed to be 0.05, and sigma of p hat is equal to 0.05, 0.95 over 25 square root, which I'll calculate in a moment. But these are the assumed population mean and standard deviation, or sampling standard deviation. And again, I say sampling standard deviation simply because the standard deviation will change depending on the number of trials that occur. And in this case, we're assuming 25 trials. So 0.05 times 0.95 divided by 25, square root of that answer. We're getting 0.0436. We're getting 0.0436. So let's see what happens. Let's just see what happens. Now, this guy, in his sample, the sample drop rate, and I emphasize sample, is p hat equals 0.20, meaning this guy was getting 20% drop rate. Huh. So now let me restate the question. What is the chance of getting a 20% or better drop rate, assuming p equal 0.05 in 25 trials? Question mark. I'm going to leave that up there for a moment. The question that I am then asking is this: what is the chance of getting a 20% or better drop rate, assuming a population P of 0.05 in 25 trials? Based on all of that information, we're assuming the sampling mean is 0.05. We're assuming the sampling standard deviation is 0.0436. And now we can actually go ahead and calculate a normal CDF. Don't forget to walk through your assumptions and conditions. Oh, Mr. Markey, you forgot to run through your sample or your assumptions and conditions. I know. I kind of did that because I'm trying to move ahead with this. But just for the sake of argument, assuming random number generator, RNG, within video games, you can assume a random sample. 25 is kind of close. 25 could be large enough. We would like it to be 30 or more, but let's just go with 25. I don't know about assume or successes and failures. Hold on a second. 0.05 times 25. Ooh, Mr. Markey, I can show you that right there. Look at that. Your expected successes are not that high. Oh, goodness. That must mean we must need like a larger number of samples or something. Yeah. What I'm doing right now is what people tended to try and argue online. People were trying to argue online that certain sample sizes were not large enough. Now, I'm going to do this calculation actually twice. I'm going to do this calculation with 25 trials, and then I am going to have to do this calculation with an appropriate number. I got to do it with an appropriate number, so let's make sure I get this appropriate number. I'm going to have to do it with 200 trials. I'm going to have to do it with 200 trials, because if I do it with 200 trials, then I would have the 10 expected successes. But let's just assume all the assumptions and conditions are met, even though I really don't think they are here. And let's actually calculate that normal CDF. It is vitally important that you talk about assumptions and conditions. Because if you have 25 trials and you're like, it's borderline large enough, I guess you can kind of accept that, and then you keep going, and then you never actually check the expected successes and failures, ooh, that's a huge red flag. Because if your assumptions and conditions are not met within reason, then your results are called into question. Your accusation at this Minecraft speedrunner is called into question because you didn't go deep enough. You didn't hit those assumptions and conditions. Thus, you're kind of invalid at that point. Let's calculate the chances of this thing happening, and then we're going to have to go ahead and do 200 trials. Well, let's just see what happens. Normal CDF, parentheses, 0.2, comma, big number, comma, 0.05, comma, 0.0436. Again, this is with 25 trials. Ooh, I don't know. My assumptions and conditions were not met. Let me see what happens here. I'm just going to type this into my calculator here so I can kind of move forward with this. Boom. Oh, goodness gracious. So let's see. This number, well, let me write it down in scientific notation. It's 2.9 times 10 to the negative fourth power. Can't even see that. I'm going to have to put another piece of paper up here. Hold on. You can't even see that. There we go. There we go. It's 2.9 times 10 to the negative fourth power. That is what that probability is. What is that? 2, 9, 1, 2, 3, 4, boom. It's like 0.00029. That is the chance of this guy getting a 20% drop rate in just 25 trials. But again, we didn't hit the assumed information that we needed to. We didn't hit the assumptions, conditions. We didn't get the number of expected successes, number of expected failures that we needed to get. If I need at least 10 expected successes with an assumed population parameter of 0.05, zooming in, I am going to have to go upwards of 200 trials, which, by the way, what I just did is how you would figure that out. You're like, oh man, there's an assumed drop rate of 5%. If I want to hit all the assumptions and conditions, I'm going to need at least 200 trials. I wonder if video game speedrunners play the game that much, he said jokingly. Video game speedrunners play thousands and thousands and thousands and thousands of times. So there's plenty of information that they could potentially draw from. So this might be invalid. And let me make a little note right here. This calculation is invalid based on assumptions, conditions not being met. And this is something that you can do to fight against false statistics that are out there if you recognize that certain assumptions and conditions are not met. When you get to the AP test, you may be faced with a situation where they describe a scenario to you, and your job is to poke holes in it. Example, 0.05 times 25. What'd that get you? Got like, I can't even remember what I got me before. 1.25. 1.25 not greater than 10 expected successes. Last time I talked about how, well, I had 9 expected successes. It's close. It's not great. If I had 9 expected successes, then, I could still move forward with that. But 1.25? No, I cannot do that. I cannot move forward with that many expected successes and assume that my conditions have been met. I'm sorry, I can't. So I have to up my number of trials. I have to go deeper into this guy's, alleged deception. The chances of him getting that drop rate are pretty darn small. But let's try it with 200. Let's try it with 200 trials. So, still going with the same program drop rate. We are going with 200 trials in order to get the appropriate number of expected, it's hard to say it over and over again, expected successes. Just calculating that up here. Boom. I have a sampling standard deviation of 0.0154, approximately. All right. It changed the standard deviation. It made the standard deviation smaller. Okay. That happens. We assume that happens because the larger the number of trials, the more normal it becomes, the more consistent the data is. Okay. All right. So let's see what happens here. Now, same question, 200 trials. Instead of asking, what are the chances of getting a 20% drop rate? I'll write it down. What is the chance of getting a 20% drop rate or better assuming P equals 0.05 in 200 trials? Question mark. Now, in 200 trials, clearly, like we said, the standard deviation is smaller, the sampling standard deviation, that is. Again, assumptions, conditions. I've talked about how we needed 200 trials. Now, with 200 trials, we do have 10 expected successes. We clearly have more than enough expected failures. We have a large enough sample size. Because of video games being random number generated, it's RNG, randomness is already there. Because of all of this, independence can be assumed, independence of one drop rate to the next. It's not like I get that special item the first time and then there's a smaller or greater chance of it happening the next time. No, it's 0.05 every time. Independence can be assumed. Let's calculate this normal CDF. Normal CDF of 0.20, comma, big number, comma, 0.05, comma, 0.0154. Let's see what happens there. Normal CDF, 0.20. Come on, you. Come on. Can't even bring this up properly. 0.20, comma, big number, comma, 0.05, comma, 0.0154. Holy crap. 1.03 times 10 to the negative 22nd power. Holy crap. That is much worse. Let's put this into context. Assuming a population mean and a sampling standard deviation based on 200 trials, the chances that this Minecraft speedrunner would get a drop rate of 20% or higher, the chances of that happening, 1.03 times 10 to the negative 22nd power. Basically, take this decimal point and move it back 22 spots. And those are the chances of that happening. The chances are so astronomically small that we are left to call into question a few things. Eventually, we're going to get to hypothesis testing. And you're going to find out when we get to hypothesis testing that it's actually the 0.05 that's on trial. Not the YouTuber, but the 0.05. But the conclusion is the same. We can conclude that, well, we have enough evidence to suggest that the drop rate is not 5%. Clearly, the drop rate's much higher than 5%. But then the logical conclusion is like, well, if the game is automatically set to 5%, then this guy manipulated the random number generator. This guy manipulated it clearly, which is, that's a conclusion that we can come to. We need more evidence than that, but statisticians do not proclaim innocence. We either claim guilt or not guilty. In this case, we could definitely say that we have evidence to suggest that this guy's drop rate has been manipulated. There is a certain threshold by which we can say whether or not a number is too small or whether it is typical to show up. The threshold, if I can spell that correctly, the threshold for determining if a probability is too small, is way too small, I should say, is 5%. If we get a number greater than 5%, then it's like, oh yeah, that's normal. That could happen. If we get something under 5%, ooh, we have evidence calling this into question. That's all I have for today. Bell just rang. That 5% number is going to make a big deal later on in the future. That threshold of 5%. Now, just one quick thing. That 5%, technically, I could give myself more credence and I could say, well, maybe I want to put my threshold at 1%, or maybe I want to put my threshold at 10%. Yeah, technically I could do that. But the typical threshold is 5%. That's usually the statistical gold standard. Okay. Next time, we will be continuing with something slightly new. But I'll get there when I get there. I will be assigning you something in regards to this chapter one more time before the end of the week. But I'll talk more about that in the future because I got to get moving to my next class. Thank you, guys. If you haven't commented in the stream, make sure that you do, because I do got to set up my next stream. So I'll give you a moment to do that before I set this thing up. Okay. I'm going to sign off then. Boop.